Hello everyone.
Good morning, ma'am. Sorry,
Good
good
morning.
afternoon.
How many of you have solved the problem I gave you yesterday? Aditya?
No, ma'am. Actually, I'm not feeling weird from few days, so I am totally not aware about what is going in the class.
You were absent yesterday?
No, ma'am. I was present, but I'm for have some network issues, so I didn't get last some points. So I have to revise those points and then I have to proceed ahead.
Okay. Ayush? Ayush, number 15. Ayush, have you solved the problem? Second problem on helical gear. Why? Do you know Ayush Patil from final year? Is present final year, I guess. Ayush Patil, present final year, he got into IIM Bangalore. 21. Okay. Let's start. Well, we discussed about spur gear, we discussed about helical gear. What is the velocity ratio used in spur gear and helical gear, Sarthak? Sarthak, what is the velocity ratio used for spur gear and helical gear? 6 for spur gear, right? 10 for helical gear. Okay. If I want to use speed reduction, which is almost say 25, 30, 40, what can I do or what should I do? Suppose from 1440 RPM motor, I want the velocity to reduce to say 35. Okay, gear train is one option, but this gear train will take a lot of space. I have space constraint. I don't have enough space for so many gears. What is the other option? Pranay? Pranay 24, you are there?
Yes, ma'am.
One option is gear train if there is no space constraint, but if there is a space constraint, I don't have enough space for the entire gearbox.
Ma'am, I'm unable to recall it.
Anybody else? Worm gear is the right answer. Give me this answer. What is the velocity ratio for worm gear, Pradyumna? Do you know? What is the velocity ratio range for worm gear? 60 to 100. It could be as high as, yes, it could be even higher than 100. If you have velocity ratio as high as 200 is to 1, 100 is to 1, 150 is to 1, the available option is worm and worm wheel or worm and worm gear. Call it gear or call it wheel. But here the two shafts will not be parallel. One of the shaft will be perpendicular to the another shaft. So what is worm and what is worm wheel? And where do you find the application of worm and worm wheel? Although we say the velocity ratio could be as high as 200 is to 1, but we rarely use it for this high velocity ratio. Because as the velocity ratio goes on increasing, the efficiency will go down. So there is a formula for efficiency by thumb rule. This is not the formula we'll be using while solving the numericals. This is by thumb rule. So thumb rule is when you just know the velocity ratio, then the efficiency is given by 1 minus 0.005 times velocity ratio. So higher is the velocity ratio, more would be this term, which is negative, and efficiency goes down. So with increase in velocity ratio, the efficiency is lesser and lesser. And so normally the range of velocity ratio that would be used is around 40, 50 to 60, not more than that. But worm and worm wheel can be used for velocity range as high as 150 to 200, even up to 250. In rare case, you can go up to 300 as well, but then as I said, efficiency will go down. It finds its application essentially in, somebody can tell me, all of you I'm sure must have seen this. You may not know that this is worm and worm wheel. This is used in lifts. It is used in elevators, hoists, cranes. The most common applications. And these are used in such application for the inherent advantage that it is giving a large reduction in one stage, large speed reduction in single stage. You don't have to use gear train or two-step reduction or three-step reduction. Another major advantage of this worm and worm wheel is it acts as a self-locking screw. So wherever you stop rotation of wheel, worm, this will stop rotating. You don't have to have another locking arrangement. The operation is quite smooth and silent. And it is very compact as compared to an entire gearbox or a gear assembly. This is quite compact. So how does this look like? It would look something like this. This is the worm. like a screw thread, which is rotating on a shaft here. This is its side view, and this is the wheel or the gear. This will have gear tooth, and this is usually a helical gear which will mesh with the worm. The side view of this gear wheel or the worm wheel will be a rectangle, and the side view of this would be a circle. This is known as worm, which is usually the input. Usually the input shaft will be worm, or this is the driver rotating in this direction, going inside the plane. Depending upon the left hand or the right hand thread, this will be the wheel connected to the output shaft or the driver shaft. Wheel or the gear. And for the worm and worm wheel design, we will usually design only the gear. We have to design only the gear from the module or the circular pitch of the gear. We will get what is the pitch for the worm, and the remaining data for the worm is directly given in the design data. So we don't have to worry for design of worm. All we have to design is only wheel, and we'll be again designing using the Lewis form factor expression. So this has all the advantages: large reduction, axle, self-locking screw, silent, smooth, but it must be having some limitation, right? So its biggest disadvantage or limitation is the efficiency is not very high as compared to spur gear or helical gear, where the efficiency is almost 95 to 98%. The only disadvantage with this is efficiency is low, and the efficiency further gets lower and lower with increase in velocity ratio. And there is one more disadvantage, if anybody can point out. Can somebody tell me? So its first disadvantage is efficiency is low, or it depends more upon the velocity ratio. And second disadvantage, cost. Yeah, a little more than helical gear. Another one, more heat. Yes. The another basic disadvantage is there is lot of heat generation. Lot of heat generation, and so while we are designing the worm and worm wheel, we have to design it for two concepts. One is it's designed for mechanical strength, like we design the gear, we check for its bending, we check for its wear, we check for its endurance strength. So the design is done based on strength, and it is also done based on the heat dissipation or the heat transfer, how effectively the heat is dissipated. If the heat is not dissipated, then the efficiency will further go down, it will not be very effective, or there would be huge losses. So for design of worm and worm wheel, you have to design it for both strength and heat dissipation. Now, like these two are mechanical components continuously rubbing against each other. Same is true with spur gear and helical gear also. Why do you think this has more heat dissipation? Yes. Why do you think this has such a big issue of heat dissipation? Anybody? Different geometry. Okay, not only geometry, because of rotary and translatory motion. Yeah, so to be precise, more than rotary and translatory, this screw on this worm and this tooth, they are more like sliding over each other, which is not the case in case of spur gear or helical gear. They are not sliding over each other. Although they are coming in contact, and after it leaves the path of contact, the contact is broken. But here, since the gear tooth is sliding along the surface of the wheel, there is large amount of friction, and also another reason is there is huge relative velocity. Yes. Relative velocity is very high. This is another important question from interview perspective, and this was asked to me during my one of the interviews of promotion, why there is a huge heat dissipation, and the reason is large relative velocity, and this relative velocity is in direction. So this is having a relative velocity perpendicular to this because it is rotating, say, going inside the plane from here, and this has a relative velocity in this direction. So a relative velocity need not only be in magnitude, it can be in direction also. Since the worm and the worm wheel, they are rotating in two different planes, their axis of rotations are perpendicular. So there is a huge relative velocity in direction which leads to heat dissipation. So this is an important point which you must remember. And to reduce this heat dissipation, we have to take care of the friction between these two material, or the friction between the component. And to reduce this frictional force, the worm wheel is made out of a material with very low coefficient of friction, and it is always made out of phosphor bronze. You don't have to worry for the material selection. We'll always go with phosphor bronze. Phosphor bronze is a nickel chromium alloy, and the value of coefficient of friction is very small, of the order of 0.0025. So why only phosphor bronze is used as a material for worm wheel? Another question. So the answer is because it offers very low coefficient of friction, the frictional force reduces, and it reduces the amount of heat which is generated. And for heat dissipation, we use different ways to ensure that heat is properly dissipated. So for effectively dissipating heat, one is the material selection. We have already selected a material with very low coefficient of friction. Second thing that we are doing is we'll make sure there is a large surface area for heat dissipation. So we'll also calculate what is the area available for heat dissipation, and if you, by calculation, if you see that the heat generated is more than heat dissipated, we increase the cross section, we increase the diameter for the worm or worm wheel to improve the surface area. What else is done for heat dissipation? What is normally done in vehicles or in engines or in machines for heat dissipation? Fins. Yes, that is one of the ways, but yeah, oils and coolants. So large amount of lubricant or coolant is added. So we will be using lubricants and coolants for heat dissipation. So as you know that the power transmission or the power transmitted depends upon torque and the angular velocity. Since we are reducing it from 1440 RPM motor at the input shaft to a very low RPM of almost say 40 to 50 RPM, the value of omega goes down, and for the same power, the torque would be pretty high, very high torque, because P is constant, the moment omega goes down, torque is high. And so this worm and worm wheel is also used in applications where there is a requirement of low speed and high torque. Low speed, high torque. Can you give me one more example other than this cranes and hoist? You have studied in your previous semester, probably fourth semester. Very high torque is required, and you want the shaft to run at very low speed. And the example is rolling mill. Rolling mill where it has to roll from a huge ingot to a bloom or a billet, or from a billet to a wire or a thin rod. So there is a huge reduction of cross section of a metal. Normally it is high temperature rolling. Normally it is cold rolling also. Torque required is very high, and this is done at very low speed to improve the surface finish. If you do it at high speed, the surface finish is poor. One specific application, the only example where the worm and worm wheel is used in automobile is it is used in the differential gearbox. Differential gearboxes used in automobiles for taking a turn in one of the models of Audi. If I am not wrong, this Quattro model of Audi, and its differential, this is used. So a worm and worm wheel looks something like this. This is the worm wheel or the worm gear, and this is the worm. So this worm is continuously rotating in both the directions. So another example of another application of this is it is reversible. This can rotate in clockwise and anti-clockwise direction, and so this also rotates in clockwise and anti-clockwise direction. Every time you are lifting the weight up or lowering it down, the lift goes up or the lift comes down, this starts rotating in opposite direction. So this is the real life application. I don't know how good an observer you are, but in all the cranes and the hoist applications that you can see in and around wherever construction is going on, this kind of arrangement will be seen. So this is a worm, this is a wheel, this will be highly lubricated with oil or grease. A very simple example, if you have enjoyed playing with such kind of toys, here you can see this is also a worm and a worm wheel in a small toy, do-it-yourself kind of kits where such parts would be available, and then a manual is given and you can assemble it all by yourself, where this assembly is already given. You have to just place it in position. How many of you have played with such kind of toys? Richa, Prajwal, Karthik. Anybody has played with such kind of toys? Devansh? Yes? So I'm sure you have enjoyed such kind of toys also. So these are worm and worm wheel, which, as I said, you must have seen in number of different applications. So while we are working for the heat dissipation concept, all we need to calculate is what is the rise in the oil temperature for our heat dissipation. For strength design, we know we will be using again the bending strength, the wear strength, and endurance strength for the gear. For heat dissipation, we'll be using an oil or a coolant, and we are checking for what is the rise in the temperature of oil. So there is a permissible range. If the rise in the oil temperature is 60 degrees, 70 degrees, it is okay. Yes, in grass cutter also you will see this. Saurabh, you are right. Oh, I missed this message. So how much the temperature of oil is rising, this depends upon what is the amount of heat generated and from the surface area, and the center distance will be measuring what is the heat dissipated, and we will equate this assuming the heat dissipated is more than or equal to heat generated. So heat generated will normally depend upon what is the rated power. So we'll have an expression for efficiency in terms of the other known parameters. So if the rated power is PR, heat generated is always calculated based on the rated power. 1 minus efficiency times the rated power. This is converted into heat. So this is all in watts. And the heat dissipated, this will depend upon the coefficient of heat dissipation, the surface area. This is del P, and the rise in temperature. So this will normally equate, and we'll find out what is the heat dissipation. So if rise in the oil temperature is 40 degrees, 50 degrees, we say this is well within the range. And this power rating this power from heat dissipation point of view, this is a formula for power only from heat dissipation point of view. We will not be using this formula for rated power anywhere else. This is like an empirical formula which depends upon what is the center distance, where center distance C is taken in meters, C raised to 1.7 upon the velocity ratio. How much is the velocity ratio? Plus 5, where power is in kilowatt. This formula is not given in design data book, and so I want you to take it down. C is the center distance. Center distance between what? Which center distance? VR is the velocity ratio. Worm and the gear. Larger the center distance, more effectively the heat dissipation would be done. Now there are three different assemblies or three different arrangement of worm and worm wheel. This first one is the most easily available one, where this is the worm and this is the wheel, and you can see that there is a point contact between the wheel and the gear tooth. What will happen for the point contact? The amount of force that is transmitted, Ft, is pretty high, whatever is the value, and this entire force is coming on a single point. What will happen to the stresses? For effective stress distribution, we want the larger contact area. So if it's a point contact, the stresses would be huge. So with point contact, there is heavy stress at the point of contact, and so the power transmission capacity becomes restricted. The amount of power it can transmit, this is limited. With this simplest of the design, and this design is known as no overlap. Please take down this figure in your notebook. Now this is the second design. If you can appreciate the difference in this, the gear, instead of having a flat surface like this, the face width of the tooth is cut in this particular shape. So this is the shape of the gear, and this is enveloping the wheel. This gear surface is enveloping the wheel, and this is known as single enveloping worm and worm wheel. What is the advantage of this? This is known as no enveloping or no envelope. Why do you want this to envelop this? Why do you want the wheel to envelop the worm? So that the contact improves. Instead of point contact, now this is a line contact. And with point shifted to line, the stresses would reduce. Gear is enveloping the worm. Gear envelops the worm. And look at this third kind of assembly. Worm is enveloping the gear and gear is enveloping the worm. So both worm and wheel, both of them are enveloping each other, and this is known as double enveloping. Double enveloping. And here, from point contact to line contact, now this is area contact. And with area contact, here the power transmission capacity is large as compared to the first two cases. Large power can be transmitted. What would be the limitation here? Any limitation here? Large power can be transmitted. Friction will increase, yes, because there is an area contact. Lot of friction, so more heat dissipation. What else? What else? Other than friction and heat dissipation. See how you are biased, because we just spoke about heat dissipation. So any other design and disadvantage, you will get only heat dissipation and friction. और कुछ सोच के देखो, what else would happen? Yeah, somebody please. You have to just guess. Yes, difficult for manufacturers. Yes. So not the construction, but the assembly. This mounting or the assembly has to be very precise. This requires very precise mounting. And it is very difficult normally to get an assembly of this. So gear and a worm, or worm and worm wheel, this will always come in an assembly. So even for that toy, you will get that part already assembled. So it would rarely be a situation where, like in spur gear or in helical gear or belt drive, you get worm from one supplier and wheel from another supplier and assemble. That is never done. So worm and worm wheel will always come together in an assembly, so that the center distance, the curvature for this enveloping is already done, checked, tested at the manufacturer, because this requires very precise mounting. So it's manufacture and assembly. This is really a challenge. Assembly is difficult. Should we proceed? Or you want me to go back to that same? Okay. So now this is the wheel. This is the wheel, the worm diameter. I have taken this. I have taken the drawings already pasted there, because here with such a smooth board where writing A, B, C, D itself is difficult for me, getting the perfect drawings is all the more difficult. But this can be drawn easily on a blackboard with some friction. But you are expected to draw this. This is DW. So DW is the worm diameter. This angle is known as the lead angle for worm. This distance is known as axial pitch. Axial pitch is the distance between any two consecutive points on the adjacent thread taken along the length or along the axis. So PA is known as the axial pitch for worm. DW is the diameter of the worm. And here we have, if I'm measuring from this to this, what is this distance known as? Here to here or center to center, what is this distance known as? Yes, Saurabh? Shravya? What is the distance between any two corresponding point on the adjacent tooth known as? Circular pitch. So if PC is the circular pitch for gear or the wheel, for this to mesh, like for two gears to mesh, modules should be same. For worm and worm wheel to mesh, the axial pitch of the worm must be equal to the circular pitch of the wheel. This is the important criteria for these two to mesh. If the gear has module M, and what is lead in case of a screw thread? What is lead? don't know in which subject you have studied. You must have studied in theory of machines 1. स्क्रू जैक डिजाइन किया होगा ना, पावर स्क्रू डिजाइन किया होगा. Or in machine drawing also you must have studied about various kind of screw threads. Distance traveled in one rotation. Yes. What is the development of a helical screw? If you open it, what is the shape you get? Wedge, spiral. It gives you a wedge shape or a triangle. So if I open this screw, this will be always a right angle triangle, which is if the distance traveled is equal to the circumference. So in a distance equal to the circumference, it lifts up by a height equal to lead. L. And this angle is known as the lead angle, lambda. Or we say that tan of lambda is lead L upon pi dw. So lead is the distance traveled in one rotation of nut. So if this is a screw thread and if there is a nut, in one full rotation of nut, which is equal to the circumference pi dw, this will travel a distance from here to here or here to here. So pitch is equal to lead in a single start thread. Lead is equal to 2 times the pitch in a double start thread, or lead is equal to 3 times the pitch in a triple start thread. And so the number of starts is counted and we call lead as its axial pitch into number of starts. So TW is number of starts, or we also call it as number of teeth on the worm. So normally a worm will have 2 or 3 teeth, not more than that. So number of teeth is same as number of starts. So number of teeth, because we are checking with its velocity ratio, so we are also calling it as number of starts. Normally this will be 2 or 3. So normally this lead angle lambda would be 6 degree per thread. This will be again given in our design data book. Or if it's a single start or a single start thread, minimum value of lambda would be 9 degrees. In case of double start, this could be 6 degree into 2. In case of triple start, this could be 6 degree into 3. So it could be 12 degree, 18 degrees likewise. But if it's a single start, then this cannot have a minimum value of 6. So minimum value is 9 degrees. For double start, triple start, the value can be 6 degrees into number of starts. So this is if no data is given in the problem. There is a term known as diametral quotient. Now in different books, the problems are given in different terminologies. Only in case for worm and worm wheel, you will get more number of solved questions in machine design by Bhandari. For no other topic, I normally refer Bhandari, but only for this particular topic, you will get number of solved questions. So there is a term called diametral quotient Q, and this is equal to dW, which is the diameter of the worm, upon M, which is the module for the gear, dW by M. This is known as diametral quotient Q. And I am now rewriting this expression of tan alpha, which is lead upon pi dw. Now lead is equal to the axial pitch for a single start thread, and for the worm and wheel to mesh, as I told you, this PC should be equal to PA. PA is equal to PC for a single start thread, but for a double start thread or for a triple start thread, this is equal to number of start into axial pitch. And so this lead will be equal to circular pitch in case of multiple start thread. So the lead, which is equal to PA into TW. Now I am rewriting this expression of tan lambda, where lambda is a lead angle. And this is the angle of a right angle triangle whose height is equal to lead and whose base is equal to circumference of the screw. So lead I am writing as PA into TW upon pi into dw. From here I am writing as m times q, where q is the diameter quotient. Axial pitch is pi times module into tw upon pi times module into q. So this comes out to be number of start of the wheel upon the diametral quotient. This is tan lambda. So these equations we'll be using later on. Save them for the future use. So in some of the problems, as I said, different books will have different way in which the problem is given. There's a designation of worm gear, and the designation would be worm, and worm gear is slightly complicated in design, but you will appreciate its beauty depending upon how well it is used in transmission of torque for cranes, overhead cranes. So it would be something like 2/24/5/3. A worm gear with this designation. So what is this 2/24/3/7? So this will be, the first term will be number of starts in the worm. Second term would be number of teeth on the gear. Third term would be the diametral quotient, which is dw by m, and m is the module, where tan of lambda would be 2 tw by q. So these are some of the terms that we'll be referring to or will be using later on. In the next class, we'll talk about what are the forces and how they vary in magnitude and direction. It will be a long derivation, but just for understanding, here when this wheel is rotating, say in anti-clockwise direction, and this is going inside the plane, here this is the Ft force responsible for power transmission. What is tangential force for wheel? For the worm, this becomes axial force because now this is acting along the axis. So Ft for worm, G, gear, will be equal to axial force for worm. Whatever is the axial force along the axis of this, perpendicular to this board, because this is again a helical gear, so this would have an axial force. So whatever is axial force for gear will be what for worm? Axial is perpendicular to this plane. The axial force for the gear acting along the axis of gear would be what force for worm? Manan? Daitva? Daitva, you are there? Hello? Pratyusha? Okay, am I audible? Yes. Whatever is axial force for this acting perpendicular to the plane here becomes a tangential force for the worm. Like tangential for the gear is axial for the worm, like axial for the gear will be tangential for the worm. Tangential for the gear would be axial for the worm. And only the radial forces will remain the same. Whatever is acting radially here is also acting radially to the worm. And what is the magnitude? This we'll see in the next class. So next class we'll start from here. How the axial force for the worm is same as the tangential force for the gear, and how the axial for the gear becomes the tangential for the worm. Which one is a desirable component of force out of all these forces? Which one is a desirable component? FTG, the tangential force on the gear. This is the required force or the force which is responsible for power transmission. So we'll see how there are so many components, because now here this tangential component or the axial component will act along the helix angle, and it will have its component along the helix angle lambda. So you will have a coefficient of friction also. For spur gear, we don't take friction into account. For helical gear, we don't take friction into account because there the actual sliding of the gears is very less, and so the friction is less, heat dissipation is less, losses are low, and so the efficiency is as high as 98%. But here we have to consider the heat dissipation, we have to consider the frictional losses, so we have to also consider the component of frictional forces apart from other forces. And so I am repeating, this topic is slightly complicated after spur gear and helical gear. So I request all of you to be very attentive in this particular topic that we are discussing today and tomorrow. Tomorrow, do we have a class? No, we don't have a class tomorrow. Okay. So Saturday we'll again have a class 4 to 5. I again repeat, for those who in their feedback or response they are asking for shifting me Saturday's lecture and Wednesday morning 8 a.m. lecture, you have to give me a slot for shifting this. So that's all from my end. Do you have any questions to ask? Feel free to ask the questions for whatever we have discussed till now. Riddhima, Tanvi, Rahul, Richa, any doubts? No doubts? I really wonder how come there are no doubts. You guys must be pretty intelligent, huh? Tanvi? एक बार में पढ़ाया पूरा समझ में आ गया, there are no doubts. Really wonder. Om Prakash, on number 76.
Yes, ma'am.
Any doubts?
No, ma'am.
No. Are you sure you have listened to the entire class and you have taken the notes? Silence is taken as no or yes. Okay, whatever. Thank you all. We'll stop here. Next class will start from this part. Thank you.